The question, what is artificial intelligence, is just a phenomenally difficult one. Nobody owns artificial intelligence. It's a very broad church. Lots of people have very different ideas about what it is and what it should be. For some people, artificial intelligence is the Hollywood dream. What they're after is the idea of building machines which are as fully capable, or perhaps even better, more capable than human beings. Machines that could do everything that a human being could do. And that's sometimes called general artificial intelligence. For other people, and I'm more in that other camp, artificial intelligence is about building tools, building computers that can do very specific tasks better than human beings can. So, for example, machines that can diagnose abnormalities on a heart scan or spot tumours on an X-ray, those kinds of things. The bulk of work in artificial intelligence is around those kinds of problems. But I say it's a broad church. Nobody owns it. I certainly don't own it. You know, everybody listening to this will have their own views. But I have to say the center of gravity in AI is around extending the capability of machines to get machines to do things which currently only human beings can do. I hate the word revolution to describe these things, but I think what we've seen is genuine breakthroughs in the sense of a step change in capability of AI.
The term refers to machines, robots and software systems that perform complex tasks independently, without being given instructions for each individual step. Experts agree that AI will change our lives. Development is currently progressing at a rapid pace, but the beginnings of AI can be traced back over decades. In the summer of 1956, leading US computer scientists, mathematicians and linguists came together to conduct a research project. Their vision was to develop self-learning systems that could solve tasks requiring human intelligence. The scientists also coined a new term for this ability: artificial intelligence. The first AI program was able to prove mathematical theorems. Soon thereafter, a programming language emerged for processing symbolic structures. The AI pioneers of the 1960s were thinking big. They dreamed of creating a super machine, a general problem solver. They researched into machine language translation and developed the world's first autonomous robot. Shaky moved around jerkily and carried out simple tasks, in the laboratory at least. The first chatbot, Eliza, was developed by the German-American computer pioneer Joseph Weizenbaum. Eliza simulated the responses of a psychotherapist during a patient consultation and was deemed deceptively realistic by some. As promising as these approaches were, researchers always concluded the real world was far more complicated than the specific problems they were addressing. The initial euphoria cooled off. Research funding was withdrawn. AI winter. In the 70s, scientists questioned whether AI systems could be truly intelligent, or whether they merely simulated intelligence. The focus only shifted back to more practical matters in the early 1980s, when the first expert systems started to combine the expert knowledge of individual disciplines to assess vehicle damage, or diagnose medical conditions, for example. Travellers wanting to buy tickets could seek advice from chatbots over the phone. AI was coming increasingly to the fore in Germany too. The foundation was laid for outstanding application-orientated research. German scientists made a name for themselves, particularly in speech comprehension, imaging processing and robotics. The autonomous vehicle developed by Ernst Dickmanns was hailed as a pioneering achievement, cruising along the motorway largely autonomous from Munich to Copenhagen in 1995. However, there was still some way to go before series development could begin, and AI remained a niche subject. Then, in 1997, the world press screamed, "Robot beats reigning Grandmaster Garry Kasparov at chess." For the first time, an expert system had proven superiority over a human. As they were trained with more and more data, industrial and service robots also became increasingly autonomous and adaptable. They were evolving into self-learning systems. Since 2010, we've been
with AI capabilities, and there are three. The first of which is known as artificial narrow AI, which also goes by the rather unflattering name of weak AI. Now, on its face, that doesn't sound like a very interesting capability to start us off, but actually, narrow AI is the only type of AI that exists today. It's all we currently have. Any other form of AI is theoretical. So we can think of this as realized AI, that's the artificial intelligence we have today, and theoretical AI, which is the artificial intelligence we may have in the future. Now, narrow AI can be trained to perform a narrow task, which, to be fair to narrow AI, might be something that a human could not do as well as the AI can. But it can't perform outside of its defined task. It does need us humans still to train it. So if narrow AI represents all AI capabilities we have today, well, what else is there? Well, a favorite of memes, science fiction, and betting markets is artificial general intelligence, also known as AGI, and also known as strong AI. To be clear, AGI is currently nothing more than a theoretical concept, but here's the idea. AGI can use previous learnings and skills to accomplish new tasks in a different context without the need for us human beings to train the underlying models. If AGI wants to learn how to perform a new task, it'll figure it out by itself. Which sounds disconcerting, but look, we haven't even talked about the third type of AI capability yet, and that's artificial super AI.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify Song A. But when the choice became complicated, as in the case of Song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for Song B, if we draw a circle around the Song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of Song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency.
As you can see, he has a lot of learning to do, which is the basic story of all artificial intelligence. But it's also our story. Humans aren't born with many skills, and we need to learn how to sort mail, land airplanes, and have friendly conversations. So, computer scientists have tried to help computers learn like we do, with a process called supervised learning. You ready, John Greenbot?
Hello, humanoid friend.
The process of learning is how anything can make decisions. Like, for example, humans, animals, or AI systems. They can adapt their behavior based on their experiences. In Crash Course AI, we'll talk about 3 main types of learning: reinforcement, unsupervised, and supervised learning. Reinforcement learning is the process of learning in an environment through feedback from an AI's behavior. It's how kids learn to walk. No one tells them how, they just practice, stumble, and get better at balancing until they can put one foot in front of the other. Unsupervised learning is the process of learning without training labels. It could also be called clustering or grouping. Sites like YouTube use unsupervised learning to find patterns in frames of video and compress those frames so that videos can be streamed to us quickly. And supervised learning is the process of learning with training labels. It's the most widely used kind of learning when it comes to AI, and it's what we'll focus on today and in the next few videos. Supervised learning is when someone who knows the right answer, called a supervisor, points out mistakes during the learning process. You can think of this like when a teacher corrects a student's math. And the key difference between supervised and unsupervised learning is what we're trying to predict. In supervised learning, we're trying to build a model to predict an answer or label provided by a teacher. In unsupervised learning, instead of a teacher, the world around us is basically providing training labels. For example, if I freeze this video of a tennis ball right now, can you draw what could be the next frame? Unsupervised learning is about modeling the world by guessing like this, and it's useful because we don't need labels provided by a teacher. Babies do a lot of unsupervised learning by watching and imitating people, and we'd like computers to be able to learn like this as well. This lets us utilize lots of freely available data in the world or on the internet. In many cases, one of the easiest ways to understand how AI can use unsupervised learning is by doing it ourselves. So let's look at a few photos of flowers with no labels. The most basic way to model the world is to assume that it's made up of distinct groups of objects that share properties. So, for example, how many types of flowers are here? We can say there are 2 because there are 2 colors, purple and yellow. Or we can look at the petal shapes and divide them into round petals and tall vertical ones. Or maybe we have some more experience with flowers and realize that 2 of these are tulips, 1 is a sunflower, and the last one is a daisy. So there are 3 categories. Immediately recognizing different properties like this and creating categories is called unsupervised clustering. We don't have labels provided by a teacher, but we do have a key assumption about the world that we're modeling. Certain objects are more similar to each other than others. We can program computers to perform clustering, but to do that, we need to choose a few properties of flowers we're interested in looking at, like how we picked color or shape just now. Say I want to get a cookie from a jar that's on a tall shelf. There isn't one right way to get the cookies. Maybe I find a ladder, or use a lasso, or build a complicated system of pulleys. These could all be brilliant or terrible ideas. But if something works, I get the sweet taste of victory, and I learned that doing the same thing could get me another cookie in the future. We learn lots of things by trial and error, and this kind of learning by doing to achieve complicated goals is called reinforcement learning. So far, we've talked about two types of learning in Crash Course AI. Supervised learning, where a teacher gives an AI answers to learn from, and unsupervised learning, where an AI tries to find patterns in the world. Reinforcement learning is particularly useful for situations where we want to train AIs to have certain skills we don't fully understand ourselves. For example, I'm pretty good at walking, but trying to explain the process of walking is kind of difficult. What angle should your femur be relative to your foot? And should you move it with the average angular velocity of... Yeah, never mind. It's really difficult. With reinforcement learning, we can train AIs to perform complicated tasks. But unlike other techniques, we only have to tell them at the very end of the task if they succeeded, and then ask them to tell us how well they did. We're gonna focus on this general case, but sometimes this feedback could come earlier. So, if we want an AI to learn to walk, we give them a reward if they're both standing up and moving forward, and then figure out what steps they took to get to that point. The longer the AI stands up and moves forward, the longer it's walking, and the more reward it gets. So you can kind of see how the key to reinforcement learning is just trial and error over and over again. For humans, a reward might be a cookie or the joy of winning a board game. But for an AI system, a reward is just a small positive signal that basically tells it, good job, and do that again.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the two videos, I want to point you to a couple good
deep learning. But what exactly is deep learning? Deep learning is a subset of machine learning, which in turn is a subset of artificial intelligence. Artificial intelligence is a technique that enables a machine to mimic human behavior. Machine learning is a technique to achieve AI through algorithms trained with data. And finally, deep learning is a type of machine learning inspired by the structure of the human brain. In terms of deep learning, this structure is called an artificial neural network. Let's understand deep learning better and how it's different from machine learning. Say we create a machine that could differentiate between tomatoes and cherries. If done using machine learning, we'd have to tell the machine the features based on which the two can be differentiated. These features could be the size and the type of stem on them. With deep learning, on the other hand, the features are picked out by the neural network without human intervention. Of course, that kind of independence comes at the cost of having a much higher volume of data to train our machine. Now, let's dive into the working of neural networks. Here, we have 3 students. Each of them write down the digit 9 on a piece of paper. Notably, they don't all write it identically. The human brain can easily recognize the digits. But what if a computer had to recognize them? That's where deep learning comes in. Here's a neural network trained to identify handwritten digits. Each number is present as an image of 28 times 28 pixels. Now, that amounts to a total of 784 pixels. Neurons, the core entity of a neural network, is where the information processing takes place. Each of the 784 pixels is fed to a neuron in the first layer of our neural network. This forms the input layer. On the other end, we have the output layer, with each neuron representing a digit with the hidden layers existing between them. The information is transferred from one layer to another over connecting channels. Each of these has a value attached to it, and hence is called a weighted channel. All neurons have a unique number associated with it called bias. This bias is added to the weighted sum of inputs reaching the neuron, which is then applied to a function known as the activation function. The result of the activation function determines if the neuron gets
The people you ask for queries on websites, your smart assistants, even calls made over the internet, all of them have one thing in common. None of them are actually human. Now, you must be thinking, if they are not human, how do they manage to sound and seem so human-like? How do they respond to me so intelligently? And how are they so articulate? This, my friends, is the magic of natural language processing. What is NLP? Natural language processing, or NLP, refers to the branch of artificial intelligence that gives the machines the ability to read, understand, and derive meaning from human languages. NLP combines the field of linguistics and computer science to decipher language structure and guidelines, and to make models which can comprehend, break down, and separate significant details from text and speech. Every day, humans interact with each other through public social media, transferring vast quantities of freely available data to each other. This data is extremely useful in understanding human behavior and customer habits. Data analysts and machine learning experts utilize this data to give machines the ability to mimic human linguistic behavior. This helps save millions in terms of manpower and time, as you don't need to always have a person present at the other end of a phone. NLP is also a lot more widespread than you may realize. You use it every day in seemingly normal and insignificant situations. Don't know how to correctly spell a word? Autocorrect has you covered. Need to see if your article or thesis will get flagged for copyright violations? That's okay. A plagiarism checker will search through the web and find any...
Hi, I'm Carrie Ann and welcome to Crash Course Computer Science. Today, let's start by thinking about how important vision can be. Most people rely on it to prepare food, walk around obstacles, read street signs, watch videos like this, and do hundreds of other tasks. Vision is the highest bandwidth sense, and it provides a fire hose of information about the state of the world and how to act on it. For this reason, computer scientists have been trying to give computers vision for half a century, birthing the subfield of computer vision. Its goal is to give computers the ability to extract high-level understanding from digital images and videos. And as everyone with a digital camera or smartphone knows, computers are already really good at capturing photos with incredible fidelity and detail, much better than humans in fact. But as computer vision professor Fei Li recently said, just like to hear is not the same as to listen, to take pictures is not the same as to see. As a refresher, images on computers are most often stored as big grids of pixels. Each pixel is defined by a colour stored as a combination of three additive primary colours, red, green and blue. By combining different intensities of these three colours, we can represent any colour, which are called RGB values. Perhaps the simplest computer vision algorithm and a good place to start is to track a coloured object like a bright pink ball. The first thing we need to do is record the ball's colour. For that, we'll take the RGB value of the centremost pixel. With that value saved, we can give a computer program an image and ask it to find the pixel with the closest colour match.
Let's talk about artificial intelligence and robotics. What is it exactly? Right off the bat, you're probably thinking, a cybernetic organism with living tissue over a metal endoskeleton. Yeah. Well, this is just a small part of it. Artificial intelligence, more commonly known as AI, doesn't always have to exist in a robot. Think about a self-driving car or a space probe. Both of these are robots. Yes, robots, with varying levels of AI. And then of course you have things like Netflix or search engines, but we'll get into that a little bit later. Okay, so the two terms robotics and artificial intelligence actually overlap. But for the most part, they're quite separate. Now there are some variations of where they overlap, but generally, this is how it goes. Let's break this diagram down, starting outside with a simple machine like a vacuum cleaner. It has one function and one button to control it. This is classed as a machine, just straightforward simple. Now, to turn this into a robot, you could make it a little smaller, add some motors so it could drive itself around, and most importantly, upload the floor plan of your home. And then yes, it would be classed as a robot, going round the house cleaning up. But what if people kept moving furniture all the time? Or getting in the way? How could you get around that? Well, this is where the two overlap. This time, you don't need to upload the floor plan. No, instead, they have built-in sensors. This time round, it learns the floor plan. It learns that right outside the kitchen there is a very high traffic area, and probably needs the turbo mode. It even figures out that there's a spot right under your bed that hasn't been cleaned in a very, very long time. Now that's adaptive behaviour, that's machine learning, that's an artificially intelligent robot. Okay then, what about pure AI? What does this look like? Well, pick up your phone and ask Google to make a reservation at your favourite restaurant. But wait, isn't this just ticking a few boxes on a website? A bit simple, right? Well, yeah, but levels of AI increase when you have a really deep accent, or when it actually calls up the restaurant and speaks to them for you. Don't believe me? Try it out yourself. Check out Google Duplex. But of course there are...
Hello, and thanks for joining us for this discussion on the topic of healthcare and artificial intelligence, or AI. I'm Pamela Wu, Director of News and Media Relations here at UC Davis Health. Today we are joined by two experts on the topic of AI in healthcare, Dr. David Lubarsky, CEO of UC Davis Health and Vice Chancellor of Human Health Sciences, and Dennis Chornenky, former advisor to the White House on AI, who joined UC Davis Health this year as our first AI advisor. Dr. Lubarsky and Dennis, welcome. Thanks for being with us.
Thank you. It's a pleasure.
Yep.
I sort of want this to be a free-flowing conversation. I know both of you have a lot of really interesting thoughts on AI. And I want to start by saying that if you ask the average person what comes to mind when you say AI in healthcare, they're probably thinking of analyzing patient data, helping to make diagnoses. But there is so much more than that. How is UC Davis Health approaching AI's role in patient care and health?
Well, I think the first and most important thing to say, Pamela, is that doctors and nurses are in charge. Doctors and nurses will always be in charge of not only the decision making, but in being the partner to the patient in the decision making. And you know, AI is artificial intelligence, but it's not. In healthcare, it's really augmented intelligence. It's about giving your doctor and your nurse more tools to make better decisions for the patient.
When we talk about Gen AI in banking, there's a fine line on how to deploy it. Because on the one hand side, it's a new paradigm. On the other, the interactions that banks have with their customers typically need 100% accuracy. And there, the new technology presents a bit of a gap. The current opportunity for Gen AI in banking is less about consumer-facing tools. It's more about how to synthesize a bank's existing wealth of information to make better informed decisions, provide very personalized client interaction, and significantly automate many core banking processes. The financial sector knows a lot about its customers, but it's also subject to strict regulation and always under scrutiny for standards of accuracy, security, and privacy. Gen AI models are fairly easy to build, but in finance, the challenge is to apply them with the most impact and the least risk. That growing list of use cases includes chatbots and knowledge interface to support call center and in-branch agents, reducing call handling and training requirements. AI-generated, personalized and targeted content at scale to drive more efficient marketing campaigns. Determining creditworthiness, Gen AI can synthesize all kinds of data, structured, unstructured, from a range of sources, preparing loan decisions with greater accuracy. Surfacing information for relationship managers and financial advisors, maximizing personalized interactions. Custom software development as a co-pilot for coders, and onboarding new customers and automating paperwork.
Glass can give us new perspectives from the microscopic universe to the farthest galaxies. But before glass could do or be any of those incredible things, it was something else. Sand. We learned how to transform the unremarkable into the extraordinary. For marketers, that moment of discovery and transformation is right now, with the arrival of generative AI. Welcome to the AI Academy. My name is Alexa Zamko. I'm the Global Offering Leader for Intelligent Marketing at IBM, and as such, I do a lot of thinking, writing, and publishing about marketing technology. But at the core, my job has two parts. The first is I have the unique opportunity to work with chief marketing officers to figure out what their needs and challenges are, and how technology can help them and lead their teams to deliver exceptional performance. Now, I take that insight and industry knowledge back and share with the technical teams within IBM to help them build solutions to meet those challenges. Today, all of my conversations increasingly revolve around AI, specifically how generative AI is going to change marketing, how we work, how we create, and how we deliver exceptional experiences for customers. Marketing has come a long way from the decades of mass advertising and untargeted direct mail. AI and technology have helped marketers be more precise as to who we reach out to, with what message, and offers that we...
I want to start off with talking to you about 3 things that keep me up at night, right? 3 things. The first, and it may be, very common for you too, is climate change. Climate change absolutely keeps me up at night. The second thing that keeps me up at night is that people may have no idea that an artificial intelligence is making a decision that directly impacts their lives. What percentage interest rate you get on your loan, whether you get that job that you applied for, whether your kid gets into that college that they really want to go to. Today, AI is making decisions that directly impact you. The third thing that keeps me up at night is even when people know that an AI...
Hi everyone. Welcome to our second Hot Topic lecture in 6S191, where we're going to learn about algorithmic bias and fairness. Recently, this topic is emerging as a truly pervasive issue in modern deep learning and AI more generally. And it's something that can occur at all stages of the AI pipeline, from data collection all the way to model interpretation. In this lecture, we'll not only learn about what algorithmic bias is and how it may arise, but we will also explore some new and exciting methodological advances where we can start to think about how we can build machines capable of identifying and to some degree actually mitigating these biases. The concept of algorithmic bias points to this observation that neural networks and AI systems more broadly are susceptible to significant biases, such that these biases can lead to very real and detrimental societal consequences. Indeed, today more than ever, we are already seeing this manifesting in society, from everything from facial recognition to medical decision-making to voice recognition. And on top of this, algorithmic bias can actually perpetuate existing social and cultural biases, such as racial and gender biases. Now, we're coming to appreciate and recognize that algorithmic bias in deep learning...
When you first dive into the field of interpretable machine learning, you'll notice some very similar terms flying around. We're going to discuss one definition and hopefully clarify some things. That is the difference between an interpretable model and an explainable model. Although, I should warn you, there is no consensus. Part of the problem is that IML is a new field. Definitions are still being proposed and debated. We can't even seem to decide on the name for the field. Is it interpretable machine learning, IML, or explainable AI, XAI? So we'll focus on one potential definition. We will learn how to classify a model as either interpretable or explainable using this definition. We'll also discuss the related concept of interpretability. To end, we'll discuss the problems with this definition and why it's actually probably not necessary to classify models using it. If you missed some details or want the references for the information in this video, make sure to check out the article linked in the description. Also, if you're interested in IML, make sure to wait till the end of the video, where I explain how you can get access to a Python SHAP course.
Over the past couple of months, large language models, or LLMs, such as ChatGPT, have taken the world by storm. Whether it's writing poetry or helping plan your upcoming vacation, we are seeing a step change in the performance of AI and its potential to drive enterprise value. My name's Kate Soul. I'm a senior manager of business strategy at IBM Research, And today I'm going to give a brief overview of this new field of AI that's emerging and how it can be used in a business setting to drive value. Now, large language models are actually a part of a different class of models called foundation models. Now, the term foundation models was actually first coined by a team from Stanford when they saw that the field of AI was converging to a new paradigm, where before AI applications were being built by training maybe a library of different AI models, where each AI model was trained on very task-specific data to perform a very specific task.
Future of it, where we are, the challenges of it, safety, and so much more. And we are here with demonstrably one of the OGs of the AI world. Mustafa Suleyman is the CEO now of Microsoft AI. He spent more than a decade at the forefront of this industry before we even had gotten to feel it in the past couple of years now. He co-founded DeepMind back in 2010. That was later acquired by Google. In 2022, he co-founded a company called Inflection. He did that with Reid Hoffman, and then recently moved that company inside of Microsoft and is now the head of Microsoft's AI efforts. So thank you so much for being here. And just as